So in our last video, we talked about how to create Bohr models for the atom, and we actually talked about a specific pattern that was arising from the periodic table, where we noticed by doing the hydrogen, helium, lithium, beryllium, carbon, fluorine, we also did sodium, and then we did chlorine, and we also did neon. When we did these atoms, we actually figured out that there was a specific pattern arising from the periodic table. The columns of the periodic table, especially on the old nomenclature columns, which are the 8 family columns, which include these columns which I'm highlighting here, and especially if you ignore the decimals and you count them 1, 2, 3, 4, 5, 6, 7, and 8. The columns of the periodic table will tell you information about the number of electrons on the last shell that the atom has. So in other words, how many valence electrons that atom has. Well, the rows of the periodic table, like this, will be telling you how many shells the atom actually has. So that means if I pick any random atom, like for example calcium, with an atomic number of 20, okay, I notice it's going to be on the second column and on the 4th row. I can say for sure it's going to have 4 shells, so it's going to have K, L, M, and N, and on the N shell it's going to have 2 electrons on its last shell. So let's actually draw that so that we can refresh what we learned in the last video. So calcium has 20 protons, which means it's going to have 20 electrons if on a stable state, which means you're going to need, according to our prediction, several shells. So let's see how that actually looks like. Let's put a few shells. Start with 2 or 3 and see how much we got. So now if we put those electrons there, I'm going to draw them in green, and on the first layer you're going to have put 2 electrons on the S subshell of layer 1, which only has 1 subshell, level 1, and then on level 2 you get 2 subshells, the S and the P. The S will take 2, the P will take 6. It has 3 orbitals with 2 electrons each, and so you're going to put up to 8 on our next layer, 2 on the S shell, and then 4 more in the actual P subshell. So you're going to have a total of 1, 2, 3, 4, 5, 6, 7, 8. And by now you have a total of 10 electrons on that atom. But you got to keep going because you got to put all the way to 20. So now the level 3 it will have 3 subshells, and you're going to start with the shell S where you can fit 2, just like before. So you're going to put 2 more over there. So we're now up to 12. And then you're going to do P level, this P subshell level 3, where you can fit up to 6 more electrons. And so let's put those 6. You put 1, 2, 3, 4, 5, 6. We already have 8 on that level. Now remember, level 3 can actually take up to 18 electrons. But we're not going to continue on level 3 because you see, the thing is that the level 4S has less energy than the level 3D has. So instead of going to level 3, the electron will assume its next lowest possible energy level. It's very hard for electrons to be in d orbitals. And so instead of going to that d orbital, next it's going to go to the 4s orbital and fit there. So you're going to put 2 electrons maximal on that 2s orbital. Now remember, we had 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is going to be 18. We need to put 2 more, and we're not going to put them on level 3, which could still fit electrons on a D subshell, because the 4s subshell is considered a lower level of energy than the D subshell of the level 3. And so you're going to put those last 2 electrons actually on the S subshell of level 4, which means it's going to look like this. And you're only going to ever actually put more electrons on the D subshell if you actually have need for more, and that's where you're going to get the elements of the transient elements of the periodic table, which are here between calcium and gallium. But once you actually get to gallium, you're going to go back to filling in the p orbitals, this time the 4s orbitals. So you see, that's why the last electrons on the middle here are always going to be on the D shell, and the last electrons on this pair here are always going to be on the F shell, for several similar reasons as well. So you see how that's how the patterns of the periodic table figure themselves out. But remember, an important distinction is that every single atom on the last column of the periodic table, the very last column of the periodic table, or the noble gases, will have completed last shells. Their last shells are going to be completely, utterly full. So to demonstrate that, let's actually do krypton, which is element 36. It's going to be on our 1, 2, 3, 4 row and on the last column. So we expect a full subshell with 8 electrons in it, and we also expect that to have 4 shells. So let's see how that's actually going to look like. Alright, so krypton, and remember, it's going to have 36 protons. So let's do krypton with 36. Now, it's going to have, we said, 4 layers, right? So let's go ahead and put those 4 layers. Remember, these are not actually circles. They're more like ellipses. So it's okay if you don't draw them as circles, because they're not really circles. Now remember, 2 electrons in the first shell. We completed the s orbital already. Now you're going to put 2 more electrons on the next s orbital. So you're going to go 1, 2, and then you're going to put 6 electrons in the 3p orbitals. So 1, 2, 3, 4, 5, 6. You got yourself 10 electrons total. You completed the next last subshell. We can only take up to 8. So you're going to go to level 3 where you're going to put 2 more. So you're going to put 2 more on level 3. You're going to put 1, 2 that completes the S shell of level 3. Now you go to the P orbitals and you're going to put 6 more. So let's go put 6 more. You're going to put 1, 2, 3, 4, 5, 6. And you see that now, but at this time you already have 18. Now if you're going to put 2 more, you're going to go to 4S because it has a lower level of energy than 3D has. So then you're going to put 2 more over here. So you put 1, 2 on the 4 level. Now we're going to go back up here to the 3D and 5 orbitals in a D subshell. Each orbital, as usual, 2 electrons each, which means you can put up to 10 electrons on the D subshell, which means you can put 10 more electrons on our last layer. And that's right, because you see, the last layer can take up to 18. So level 3 will have 18. So like a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you actually count, you will see it has 18 electrons on the last third subshell, which is actually going to be full now. So now I have to go to back to the fourth level, and you see how I'm going down the triangle here. And now I have to put a lot of electrons because I put 2 on the first layer, 8 on the next layer, and then the maximum of 18 on the third layer. I maxed out 3 layers. And by now I have 28, but I got to go all the way up to 36, which means with these 2 that I have already at the 4S, I need to put 6 more because that's what I have to put up to 36. So that means now I have 2, 8, 18, that's 30 plus 2, 32. I'm missing 6 to get to 36. And that's exactly as many as it will fit in the p orbitals of the 4th layer. So there you go, 1, 2, 3, 4, 5, 6. And now I have ended this atom on a shell that is completed. Every shell that I have tried to fill in has been completely filled in. And that's the characteristic of a noble gas. Its last electron shell, in this case the P subshell on the 4th level, is going to be completed. And so that is the patterns of the periodic table that you have to know about. Now all the other elements want to be like that, electrically stable. Let's talk a little bit more about this. So you see how you can actually use this pattern to actually figure out the atomic structure or the electron cloud structure of the atoms. And the periodic table would then therefore tell you information about the conformation of the atoms. Now remember also that we talked about the fact that all the elements in the first 2 columns, because they only take up to 2 electrons in the last shell, they're only going to fill in the s orbitals. While all the elements on this side of the periodic table, because they will take between 3 and 6 on the last shell, they'll fill in their p orbitals. Now the ones in the middle here, we didn't really included them because these elements will be a little more complicated and they will finish with F and D orbitals. And so they will have variable valences which cannot be predicted as easily just by looking at the periodic table. You have to know other techniques to do that. And when you go to chemistry class, you'll learn about to do that. But what I want you to know is this. Looking at the S block and the P block, you can actually use the periodic table to help you figure out the number of electrons on the last shell as well as the number of shells that that atom has. Now, what is interesting about this is as you go to the right of the periodic table, from hydrogen all the way to helium, you're increasing the number of electrons in the last shell because hydrogen will have 1 and helium will have 2. And that completes the S shell. And so that's why the helium will be here as at the end of the family here as the noble gases, because he has the completed shell. Now lithium will actually have 1 electron on the last shell and 2 shells. Then you go beryllium will have 2 electrons on the last shell. Then boron will have 3. carbon will have 4, nitrogen will have 5, oxygen will have 6, fluorine will have 7. So you see how the numbers are going up as you go to the right, and then neon has 8. And when you get to neon, you have a completed p shell. And that's what makes neon interesting. You see, his valence shell, the very last shell of neon, is completely full, which means neon has an electrically stable last shell. Remember, we talked about this in a previous video. It doesn't have a fluctuating charge because its last shell, its valence shell, is completed. And that was what makes neon so special. Now, look at sodium. We'll have 1. Magnesium will have 2. Aluminum will have 3. Silicon will have 4. Phosphorus will have 5. Sulfur will have 6. Chlorine will have 7. And argon, again, will have 8. But you see, this time, all of these elements will have 3 shells. But again, when you get to argon, the p orbitals are completed. The p subshell is full. It's an electrically stable electron cloud. So all the elements on the right side of the periodic table, those noble gases, will have completed electron clouds on its very last subshell. What that means is that they're going to be chemically stable. They don't care to react with other elements because they don't have a transient charge, so they don't really want to get rid of anything because they don't have it. But what about fluorine, sitting right there, really close to neon? 1 more electron on his last subshell and he will be happy, just like neon. With 1 more electron, fluorine will be complete. Now that's why fluorine wants to take electrons. He would love to have just 1 more electron, because if he had that 1 more electron, his electron cloud would be just like neon. So he wants to jump by 1 electron so he can become like neon. What about oxygen? Same kind of thing, except that he needs 2 to jump to become like neon. What about nitrogen? Kind of like the same thing, but he needs to jump 3 to become like neon. So, because you have 7, you need 1. Because you have 6 in oxygen, you need 2. Because you have 5 in nitrogen, you need 3. What about the people on the left side of the periodic table? Well, for them, it's going to be easy to actually give away electrons. Because you see, if lithium gives up a single electron, he actually becomes just like helium. You see? So by giving up 1 electron, he becomes like helium. Beryllium, well, if he gives up 2 electrons, he becomes just like helium. Boron, if he gives up 3 electrons, he becomes like helium. And what about carbon? Well, carbon has 4. So he's going to be right in the middle. So he's going to be equally likely to give up or take electrons in order to become electrically stable. You basically get rid of his last electron cloud. Look at chlorine, for example, with 7 on its last shell. What about him? Well, of course, it's going to be easier for chlorine to take 1. Sulfur will want to take 2. Phosphorus will want to take 3. Same pattern you saw before. Silicon has 4. It will be equally likely to give up or release or give up electrons. Aluminum with 3, it's easier for him to get rid of those 3, so he will end up with 2 plus 8 and be just like neon. Magnesium will be easier for him to give up 2, and sodium will be easy for them to give up 1. So you see, everybody in the first column of the periodic table is looking to give up an electron. Everybody in the second column of the periodic table is looking to actually give up 2 electrons. Everybody on the column 13 is looking to give up 3. Everybody in column 14 can either give up or take 4. Everybody in column 15 is looking to take 3. Everybody in column 16 is looking for taking 2. And everybody in column 17 is looking to take 1. Everybody in column 18 is happy already. And that's the noble gases that everybody wants to be like. Everybody wants to be noble and complete. And so this helps you understand why atoms engage in the chemical reactions in the way they do. They do so because they want to have complete electron clouds. And the specific way in which they react depends on how their electron cloud looks like. How many electrons extra or missing they actually have. Which means the elements in the first column will all act similarly. Elements in the second column will all act similarly, and so forth. And so you see, the electron shell of the atom will give you information about the chemical properties or the reactivity of these elements. Now, we're going to revisit this topic when we talk about the periodic table patterns a little bit more. And at that point, I hope you guys see visually more what I'm talking about here. So for now, remember, by designing the Bohr models, you can see the patterns of the periodic table, and you can help you understand why elements act chemically the way they do. Alright? And remember that the rows of the periodic table will tell you the number of shells that an atom has, and the columns will tell you the number of valence electrons that electrons have on that last shell. Alright, I'll see you on the next video where we're going to start talking a little more about periodic table patterns. I'll see you guys then.